version mode, which one you are all liking more, you are just let me know. Okay. Now today, so we are going to discuss regarding linear programming problems. So this is basically a topic of class 12. Okay. So I am Michael Datta and you all are watching GANITMATICS. अब हर सवाल होगा solve. Okay. Now today, before discussing in detail regarding LPP, so in short we also call this as LPP also. Okay. Now first, the first thing that we all need to understand here is what is an optimization problem. Okay. Now let me give you all an example. Okay. Now let us consider there is a person A. Suppose there is a person, and this particular person wants to do a business. Okay. Now the business may be regarding anything. Okay. Like for example, if I consider that he wants to deal in say softwares. Okay, like software. Okay, basic softwares that we generally use in our systems and laptops wherever. Now suppose to do the business regarding software, what are the things that person will need actually? Okay. Now, first of all, let us consider that this person will need two types of softwares that he is basically going to deal with. First is software 1 and the second one is software number 2. Okay. So basically he is selling these two types of softwares, right? Now one more thing that we will consider here, that the profit on software number 1, for example, let that be rupees 10 per unit, and the profit on software number 2, let's consider that is rupees 15 per unit. Okay. Now the target of this person A is to maximize his profit. Obviously, he is doing a business, his target will be to maximize the profit. Okay. Now, but there are few things also that you need to sort out. There must be conditions, there must be few situations that you need to, like what you can say, like he have some, limitations as well. Now, obviously, we all know that for any business there needs an investment, right? So, now this person A have a limited number of resources and he have a limited number of, like you can see, he have a limited investment also, like he can't invest too much. Okay. Now for that he calculated that I can maximum buy 100 units for example. Okay, that means the total number of units that he can buy in all, it should be not more than 100. Okay, not more than 100. Keep that in mind. Now let us represent this situation mathematically in this way. Now let us consider that let the number of units bought for software 1 be X. So we are considering that he is buying X units of software 1 and similarly he is buying Y units for software 2. Okay. Then if we see the profit now, what should be the total profit in that case? Then let me denote it by a different variable, let's say Z. So profit on the first one is 10. So if there are X such units, so that means the profit should be 10X. And for the second software, the profit on each unit is 50, and if he is buying Y units, that means it should be total 15Y. That means this is the total profit that we are talking about, and this is the profit that this person wants to maximize. So that means mathematically we can represent this maximum profit in this way. So basically he wants to maximize 10x plus 15. Okay. Now since this is the basic target of this problem, this we call as an objective function. So the main target which we are representing as a linear function, that is called objective function. Now, as I told, there is a condition here. So what is it? So we write subject to. Okay, subject to means obviously we have to maximize, but there are few conditions also that also we have to take into consideration. Like for example, like as I told, that the number of units in total he will buy cannot be more than 100. So that means x plus y should be less than or equal to 100. This is the condition. Okay. Now, one more condition, if I talk or if I speak that this total investment cannot exceed, for example, say 1,000. Okay. So in that case, the investment should be 10x plus 15y. That should be less than or equal to 1,000. Okay. So that means these are the two constraints we have. This is the budget constraint and this is the number of units constraint that we have. Okay. So now this entire situation that we have basically represented mathematically, this is called my problem or the optimization problem. Okay. Then here comes the fact that what actually an optimization problem is. Now, with respect to this example, what I want all of you to understand is that not only that in the optimization problem that we are basically representing a situation mathematically, but also this type of problems got a basic, you can say a basic type or a basic, you can say a target is there. What is it? Like in this type of problems, like when I'm talking about optimization problems, basically to maximize or minimize a particular linear function. Okay. So in optimization problem, basically we either maximize or minimize a particular linear function. Okay, now we have discussed what optimization problems are all about. Now then, what is an LPP? What is a linear programming problem? Now basically, linear programming problem is basically a particular type of optimization problem. Okay. Now basically, whenever we are talking about LPP, then always keep in mind that LPP are the problems in which we basically find the optimal values of a linear function, which we have referred to as the objective function, like when we were discussing earlier, with respect to what? With respect to linear equations, either equations or inequalities. Like in the last problem, we have already seen that there were few constraints there, which we have written in the form of inequalities, right? So that means LPP is basically such problems in which we find the optimal values of a linear function with respect to either equations or inequalities, right? Now to understand this better, we will now see an example. Okay. But before that, we also need to know that what are the different type of linear programming problems that basically we are going to face in class 12. Now basically there are three basic types. The first one is called the manufacturing problems. The second one is called diet problems. And the last one is called transportation problems. Okay, we have already seen that what are the different types. Then in an LPP, we've already seen that basically it's expressing a particular situation in a mathematical form, right? So what are the things that are going to be there? Let us just see in brief. So basically in any LPP we are going to have these things. The first thing that we will have there is going to be an objective function, like the way I have showed you all earlier, right? Next thing the next thing is called non-negative restrictions. Okay, like in the last example we have seen that X was basically the number of units we were buying for software 1 and Y was that for software 2. So basically obviously X and Y should be greater than or equal to 0 because obviously we are not buying negative number of units of a particular software, right? So these are called non-negative restrictions. The third are the constraints like that we have already seen last time. And the fourth one is called the decision variables. Now decision variables are basically like X and Y. These variables are called decision variables because these are the variables that we are basically deciding the entire thing. So that's why they are called the decision variables. Okay. Now we all have discussed that what an optimization problem is, what a linear programming problem is. Now we will see how to solve a linear programming problem. Okay. Now here in class 11, you all have done inequalities, right? There we all have learned that how to find the feasible region of when we are going to have a lot of inequalities, then what is going to be the region which is bounded by them? What is the feasible region possible there? We have already discussed those things in class 11, right? So that concept we are going to use here. Okay. So we are going to see the graphical method of solving an LBP, and here we are going to use one more concept that is called corner point method. So with the help of this, we are going to find the optimal solution of a LBP. Okay. So the initial start will be something like we used to do for inequalities, like the way we have solved the graphs in class 11. We'll start it that way. But after that, there are a few more things that we are going to learn here, that how to solve, after that, how to get the optimal solution. We'll see it here. Okay. Now, so before starting with a particular problem, to understand it better, we have to first understand that what are the things that we are going to face here. Okay. Now, the first thing that we do here is that we first find a feasible region. Okay. Like for example, if in random, if I give you all an example, like for example, suppose for these two axes, suppose for example, these are the lines we are getting, okay, and suppose I'm just considering this is my feasible region, okay. So this feasible region first we have to get in this solution. Now next that we will do is, after identifying the feasible region, we have to first find the corner points, okay. So find the corner points. Now how we will find the corner points is something like this. So if this is my feasible region, then obviously this is the region which is bounded. So basically the vertices of this figure is going to be the corners. Like for this particular figure, you can see that we are getting 4 corners here. So these 4 corners you have to get it first. Okay, so you get the corner points, right? Now there are 2 possibilities here. Okay, that either you all are going to get a bounded region, which looks something like this, and you may also get an unbounded region. Okay, unbounded region is basically something like this. Like suppose the region is coming something like this. It is not going to end. Okay, there is no end to it. So both the situations are possible, right? Now if you are getting a bounded region, then your optimal solution will be on any one of the corner points. But which corner point, that we'll see in problem. I'll show you all with an example that how we are going to decide that which corner point we are going to have the optimal solution, right? Achha, but that is regarding the bounded region. But if we are getting an unbounded region, in that case, optimal solution may be possible or it may not be possible, okay? But if the solution is there, then it has to be at the corner point. Okay, so always keep in mind, whenever LBP have a solution, optimal solution will be always at the corner point, whether bounded, whether unbounded. But yes, in unbounded region, there is another case, like it is also possible that there might not be any optimal solution. Okay, but how to decide, how to know that in which case we are going to have a solution, in which case we are not going to have a solution? But obviously there is a method to check that, and there is a method to find that whether the solution exists or the solution doesn't exist. So let's now move on to the virtual board, and then let's see how it basically works. Now whatever we have learned till now, we are going to see 2 examples, one for a bounded region and one for an unbounded region, so that the concept that we were discussing, that how to solve with the corner point method, will be clear to us. Okay, so let's first start with the first one. Okay, let's see this example. Let me first make it clear to all of you that what basically we have to do here. Now this problem is that we have to minimize this function. So the function is given as minus 3x plus 4y. So this is the objective function here, and we have to solve this with subject to this given conditions, the constraints that are x plus 2y less than or equal to 8. This is the first constraint. Then we have 3x plus 2y is less than or equal to 12, and the non-negative restrictions are there. That is x greater than or equal to 0, y greater than or equal to 0. Okay. So now the way you all have solved inequalities in class 11, we are going to do it in that way. So for the first inequality, if we see, then my equation is x plus 2y equal to 8. So we'll first make a quick table for this. Okay. So taking any two values. So for the first one, let us take, say, 8, 0, 8 comma 0, and the other one let's take as 0 comma 4. Okay, no problem in that. And similarly for the second one, let us take 2 points which are going to satisfy any two random points you all can take. So for example, let's take 4 comma 0, and let's take 2 comma 3. Right, you can check that these are satisfying. Now let's plot them on the graph. Okay, so here I'm going to give you all an idea that how we are going to get the graph as. So obviously, since I'm just showing on a virtual display here, so I'm showing it without the graph paper just to give you all an idea. Okay, so let us consider that this is my x-axis, right? This is my x-axis, and let us take the y-axis here like this. Okay, pretty clear. Now let's do the marking. As I told, I'm just giving you all an idea. So I'm just taking measurements, obviously, which will not be exact as it's not a graph paper, but just consider them to be equal, and we'll just get an idea that how it should be. So I'm doing the marking here first. Now the highest value that we need here in x is 8. So we'll mark it till 8. 1 or 2 points more we can mark. No problem in that. Okay. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When you all will do, then you all will do it in the actual graph paper so that you all can get the exact graph. Okay. I'm just giving you all an idea. Okay. Negative side, although we don't need, so I've just marked 2 to 3 points here. And now on the x-axis side, we are going to do x-axis is done. Now we'll be marking for the y-axis. So it's 1, 2, 3, 4, 5, 6, 7, and here let's mark 1, 2 points. Okay, now let's mark the first. Let's see the first line, which is x plus 2y equal to 8. Let's see the points. So the first one is, let me change the color so that it becomes clear for all of you. But obviously you all don't have that option because you all have to do it with pencil. Okay, anyhow, so the first point is 8 comma 0. So this is 8 comma 0, and the next one is 0 comma 4. So these will be the 2 points. Okay, and obviously do write the coordinates there, 8 comma 0, and this is 0 comma 4. Right, now let's draw the line which will pass through them. So the line will look something like this, right? Okay, so this is the line, and you write the equation of that line, that is x plus 2y equal to 8. As we all know, for any inequality, when we do the graph, we consider them as an equation and then we plot it, because obviously we can't get it for the inequality. Okay, now the second one, for 3x plus 2y equal to 12, we have the points as 4 comma 0. This is 4 comma 0, and another one is 2 comma 3. So it will be somewhere here. That will be somewhere here. So this is 2 comma 3, and this is 4 comma 0. So let's join them. So if we join them, we'll be getting something like this, right? Let me shift the line a little bit to this side. Yes, it'll look something like this, right? Actually, now we have to check the bounded region. I hope you all know how to check that which side is less and which side is the more. So we can take a random point. Like for example, if we check for 1, 1, if you substitute in the first one, then 1, if you substitute 1, 1 there, it will be less than or equal to 8. So that means this side is the less than side. So that means for the bounded region, and that we can check for the second line as well. So that means if we check the common region, the bounded region, then this is going to be the bounded region. You all can see that I'm shading the bounded region, right? Now, if this is my feasible region, now let's see the corner points that we have. So the first corner point is this, which is 2, 3. Then 0, 4 is another corner point. Then 4, 0 is also a corner point. And obviously origin is also a corner point. So we have got 4 corner points here. So I'm marking the corner points with black so that you all can understand it clearly. Right. Now, after getting the corner point C, what we all need to do, now after that, you all just make a table like this, in which be 2 columns. On the left side, you just write the corner points. So this is what corner point method is. Let's see how we are getting the final optimal solution. And write the linear function here, which is z is equal to minus 3x plus 4y. Don't write maximize, minimize here, just the linear function. So the corner points that we have got, we'll just write them here one by one. So it's 0, 0, then 4, 0, then 0, 4, and then 2, 3. Now just simply substitute these values in the linear function, see what values we are getting. Okay, so if we substitute 0, 0, we'll be getting a 0 here. If we substitute 4, 0, then we'll get minus 12. If we substitute 0, 4, we'll get a 16. And if we substitute 2, 3, we'll get a 6. Now, our problem is to minimize it. So, what is the minimum value? It's minus 12. Very much clear, right? So, this is my minimum. Okay. And since this is the minimum, so that means this is my optimal solution for the point 4, 0. So, we'll write it, we'll conclude the problem in this way, that hence, minimum value of z is minus 12 at 4, 0. So you have to also mention that at which corner point we are getting the minimum value. Okay. So I hope now you all have understood that using the corner point method, how we are getting an optimal solution. And you all can see here that at a particular corner point, we are getting a solution, and how we are deciding by checking the value at that point. Okay. So this is the method of corner point method, and this is the way we solve it. Okay. Now this was for a bounded region. Okay. Now I will show you all an unbounded region problem. Then it will be more clear to all of you. Okay. So let's see another example. Example number 2. So let me take the problem in this way. So it's maximize z. It's minus x plus 2y. Okay. And so the conditions that are given here is x greater than or equal to 3, x plus y greater than or equal to 5, x plus 2y greater than or equal to 6, and then y greater than or equal to 0. So these are the conditions that are given to us. Okay. Now, so in the same way, first we are going to do the tables for the equations, right? So x equal to 3, we all can do it. As x plus y equal to 5, for that if we do the table, so it will be something like this. So one will be 0, 5, and one will be 5, 0. Very simple points, right? And for this line x plus 2y equal to 6, let's take 2 points for our graph. So we'll be getting, let's say, 6 and a 0, 6, 0, and let's take 2, 2. Okay, simple points is always easier to plot. Now again, let's see the graph and how it's going to look like. This is going to be very interesting. So I'm first drawing the x-axis, and then after that the y-axis. Do write there, it's very important. Last time I haven't written the x and y axis, so all of you always remember, whenever you're doing graph, it's a must to mention it. Okay. Now, so let's do the marking first. The highest value required in x is 6, and for y the highest is 5. So accordingly we'll mark. So we'll keep marking in that way. So let's 1, 2, 3, 4, 5, 6, 7, 8. Similarly on the left side, you all can mark 2 to 3 points, because negative we actually will not need here that much. Okay. and on the y-axis similarly we are marking few points, okay, as according to our requirements. It's 1, 2, 3, 4, 5, and few on the negative side as well. It's -1, -2. Okay, now let's see for the first line. The first is 5, 0. Okay, so 5, 0 is going to be here. So that's 5, 0, and 0, 5 will be somewhere here. Okay, let's join them with the line. So the line will be like this, right? Okay, so this is my first line. And for the second one, we are also going to plot, write the equation of the line here, that is x plus y equal to 5. Now for the next one, it's 6, 0. Okay, that is 1 point. And the other one is 2, 2, which is somewhere here. Let's join for them as well. So we're getting something like this. Okay, write the equation here, that is x plus 2y is equal to 6. Now again check which side comes in the greater than thing. Now after checking, we all will get that the common region is going to be this part. Let me show you all. I'm shading. This is the common region. Okay, now you all can see it is unbounded. There is no end to it. Now, how to deal with such a case, we are going to see now. Okay, now since it's an unbounded region, so what corner points we can have here? Now, obviously, there is a problem because of the unbounded region to get the corner point. So, only one corner point that we can get here is this one. As this one, right? Somewhere here you'll get it. Since I'm doing random graph, so that's why obviously it will not be exact, but when you all do on the graph, you all will see that this corner point will be somewhere near to 4, 1. Okay, somewhere will be at 4, 1. Okay, now this is the only common point we have, the corner point we have, sorry. And now at this corner point, since we have only one corner point, so we are going to check the value. Okay, now so again we are going to make that table like last time. Okay, so you write corner points on the left and write the linear function on the right, which is minus x plus 2y. So if we substitute 4, 1, then we'll be getting the value somewhere near to -2. Okay, and they told us to maximize here, so we have only one value. So since only one value, so we have no situation to compare, so that is going to be the maximum. Okay, now for unbounded region, as I was telling you all earlier, that there might be optimal solution, there might not be an optimal solution. So how to check it? See how we are going to check it. Now the method is, if the problem is related to maximizing problem, then you first write the linear equation that you already have, that is minus x plus 2y. If it's a maximizing problem, then you have to form an inequality in this way. The linear function, if it's a maximizing problem, then write greater than, and then write the value that you have there, the maximum value, -2. Okay, so we are forming an inequality. If the question is related to maximizing problem, then you first write the linear function, then write greater than, and after that you write the maximum value that you're getting. So in this case, we're getting -2. So we are getting an inequality which is minus x plus 2y equal to -2. Now plot this line on the number line. Okay, so if you plot this equation, then let's see the table. So it'll be something like we'll be getting, say, the point is going to be, say, 0 and -1. That is going to be 1 point. And another one, let's take it as 2, 0. Okay, so let's point it. So 0, -1. So 0, -1 is going to be somewhere here, right? 0, -1, and 2, 0, as we know, as here. Okay, now if we join if we join these two, then you all will find, when you all will do on the actual graph, then this will pass through the point 41. Okay, it will pass through the point 41. Now the theory here is, the concept here is, if, and you can see that the line is actually now inside the visible region. Okay, now the concept is, if this inequality that we have formed, if it have any common point with the feasible region that we have got before, that means the given function will have no optimal solution. I repeat again, if the inequality that you are forming, if it have any common region, if you have any common point with the feasible region, that means the given function have no optimal solution. But if that inequality doesn't have a common point with the region, then whatever value that you have got, that is going to be the optimal solution. So that is how we are going to check. Okay, so that means in this case, since this line already have common points, a lot of common points, you can see the line is inside the visible region. So in that case, you can write it in this way, that now line minus x plus 2y greater than minus 2 have common points with visible region. Therefore, z have no maximum value subject to given constraints. So that is how we are going to do it. Now, few of you must be thinking, then what to do if we get a minimizing problem and we get an unbounded region? Same concept, but there the inequality will be formed in a little bit different way. There what you are going to do, you will first write the linear function. For minimizing problem, it will become less than, you write the linear function, then less than, and then the minimum value that you are getting, that you are going to write, and then that inequality you are going to plot. And in the same way, if that have a common point with the visible region, then there will be no optimal solution. But if that inequality doesn't have a common point with the visible region, then that value that you have got, that corner point that you have got, that is going to be the optimal solution. So this is the concept. I hope you all have understood the concept of linear programming and how to deal in both the cases of a bounded region and an unbounded region. Okay, so that much for today. So we'll continue in some other video. Those who are new to this channel, please do subscribe and hit the bell icon. So see you all in the next video. You all are watching Ganitmatics. Ab har sawal hoga solve.